let's, hearing no major outcries from the warm-up today, everyone got 12.019, hopefully, and hearing no major outcries from the homework. Let's begin our discussion about volumes of revolution, and at some point we'll describe why these four pictures are up here. But just know that this has everything to do with chips, Play-Doh, lifesavers, and bun cake, okay? This series of lessons on volume. Today we're going to mainly focus on volumes of revolution and the simplest kind. So let's, I'll kind of walk you through a little bit of theory in general, and then we'll talk about volumes of revolution in particular. So the general idea is that you would divide some solid into a bunch of slabs. You can imagine, since this is calculus class, that that's what you would do. Divide something into lots of small things that are more easily computed. And so I have, for example, say this smooth surface, but what I'm doing is perhaps dividing it into slabs that have, I'm treating it as like it's piecewise constant on these little pieces of this, even though perhaps we're actually trying to approximate a smooth curve. Perhaps it looks like a football or something, right? So how would you approximate the volume of a football? Well, I think you would maybe do this too. You kind of make slices of the football and assume each slice is just a cylinder, a very slim cylinder. You might call it a disc or a slab or something. And each one will have a width of, let's say, delta x. And then, of course, just like as always, you would calculate each one of these as whatever the area of the cross section is times the height. That's how you calculate in general the volume of a prism or a cylinder, right? Base times height. Does that ring a bell from geometry class? That's for any kind of prism, including a cylinder, isn't it? The area of the base times the height. So if you can figure out a formula for at any x value what the cross-sectional area is, we're going to multiply that by delta x, which is, if we look at it kind of sideways, is the height. So in this particular case, we've got cylinders, but it wouldn't have to be that way. As we go to some other kinds of slices, they might not be cylinders, but today they happen to be cylinders. So eventually, as we get closer and closer to infinity, as in terms of the number of these slabs, then we of course approximate better and better whatever the smooth shape is in terms of its actual volume. So it makes sense, of course, that what we're approaching is some limit of a sum, which is an integral, which is why we're doing this in this unit. Okay, so this is A and B, which are bounding whatever the solid is. This is the cross-sectional area. And dx is, again, the width built. So this ax dx is what happens in the limit as these slabs get infinitely thin. Okay? So in the end, it's just, there's not much to say in terms of like a formula, per se. Some of you are like, okay, what's the formula? Well, cross-sectional area times dx. Now, we will provide a something slightly in the direction of a formula today. For cylinders, we can kind of develop something maybe. But that's not what I wanted. I'd like to go to this link. Oh, there we go. Now it's ready for me. Let me try and plug something like this in and see if you can. I'll go back to that slide so some people you still need something on this slide. Oh yes, thank you. I was going to come back for it, but I appreciate it. You're the best. So let's actually see if we can spin one of these around in 3D and see, just kind of see what it looks like a little bit. Maybe we can even get something that looks somewhat like this. You know, maybe we can get. How about something like x minus, well, we might be able to get this exact thing, 2x squared maybe, and we'll go from 0 to 2. Revolve around the y equals 0 line. Okay. That's not what I wanted. X minus equals -1 to x equals 3. Negative 3 to 3. There you go. Does that look somewhat like this is going to create a football? Are you ready? Okay, this is the exciting part. Let's go real slow, like. And already, by the way, this allows me to turn this around in 3D a little bit so you can see the XY plane. Okay, so here we go. This is the moment of truth. So do you see this solid we're getting? By the way, we haven't figured out how to do this yet, but it does already give us the volume of this. So somehow they're doing it, and we're all going to do that too in a minute here. But anyway, we'll play with. I have some other applets I'll show you in the coming days here. I just wanted to give you a sense of visually what we're trying to talk about here, especially as we go to do this first example. So let's consider this first example and see if we can actually come to an exact value for the volume, our very first volume of revolution. You might be thinking, oh, the square root of x, that seems like a messy function to start with. We should start with it. Y equals x. But actually, this is the very simplest function we can start with, I promise. The very first thing you should do, of course, with these problems, even though I know somebody may be resistant to this idea, is drawing. In fact, drawing is going to be a big part of this unit, is being able to visualize these things, is I think one of the biggest challenges, the geometry, the spatial visual skills needed. So this one's not too bad though, right? Of course, you know what the square root function looks like. And really, if we wanted to genuinely look at the region of interest, we would also maybe include the portion of the x-axis that we need, together with the vertical segment that connects this. So we've got this kind of shaped region here, from 0 to 4 it says for the x values. So we've got this kind of shaped region. Can you already picture what this is going to look like when you rotate it around the x-axis? Just this little nub. What will it look like? Yeah, kind of a parabolic cone of some kind, right? It'll be and actually that's the name that you might give it in your multivariable calculus class is a paraboloid. But you'll get this kind of parabolic cone. It will look like kind of the end of a spaceship or something. Or, I don't know, something like that, right? I did my best with PowerPoint tools to draw it. There you go. And then I think it's worth then thinking about, so I might draw both of these pictures, both the region and also the solid, just so we have a visual on it, the solid that you're getting. And then I would draw a representative rectangle here, just to think about Riemann sums. I think it's going to be very helpful at every point throughout this unit to be kind of going back to Riemann sum definitions of these things. And then think about not just this picture down here, but what would this slice translate to in this picture? Well, it translates to, of course, a cylinder, a cylindrical disc in this picture. So there's that slice, just that slice rotated around. And we want to think about what is the volume of that slice for a given x value. Do you think you could find it if I said 2.4, I don't know what this is right here. If x is 2.4, what is the volume of this disk? Or what is, let's say, even just, how about the cross-sectional area here? How would you do it? Ashley?
Find the y value on the 2D version.
Yeah, so plug in 2.4 or whatever this is to this function.
Yeah.
Okay.
That's your radius for the circle.
And then you know how to find the area of the circle? You do? Wow, okay, good. So yeah, exactly. I mean, we need to understand visually the thing we've been talking about here, why the y value, or the square root of x, gives the radius. That is the radius. By y, we also mean like r, right? That's the radius of that circle. So I hope you're seeing that as you look at this picture. Let's just remind everyone that for a cylinder, the volume is pi r squared h. So we need r and h, but we need those both in terms of x. We've just said that r is also just square root of x, right? That's what we mean by r. And h is, what are we calling that? Yeah, if we're looking this way, remember that's the small change in x. We'll call that delta x or dx as we go to infinity. So yeah, this is dx by y. And by y, of course, we also mean r, we also mean root x. Any of those are, for this problem, all of those things mean the same thing. All right, and then establish the limits of integration and sum the cylinders. So What are the limits of integration here? Well, we've made it obvious. Now, it's quite possible on a volume of revolution problem like these that another demand might be the demand that you've been thinking about even as recently as the world today, and that's that you might have to find the limits of integration. But here, there's no work to do. We've really, in some sense, just given it to you even in the problem. So, pretty clear, I think, that we're going to integrate from 0 to 4. What's the integrand? Before I put it up here, what's the integrand going to be? Who will take it? Pi x dx. Where'd you get the x from, of course?
Because it's from ours.
Yeah, I told you we were starting with a nice easy one, right? Because I knew ahead of time that this is going to be something that we're squaring. So yeah. So I've gone. So just at the beginning, we said we're going to integrate from a to b to cross-sectional area times dx. You don't need to write all of this, but I just want to make sure you understand that in this particular context, of course, we're talking about a circular cross-section. So we have pi r squared. We've already talked about r being root x. And so what Shivani said is right. And again, just in this unit, I'm not really very concerned with all these extra details. Just know that 0 to 4 pi x dx, I think, is a pretty easy integral. I've just done the work for you here because that's not the emphasis here. And in the end, there it is in a box. We've got the exact volume, our first one you got, of volume of revolution, 8 pi. Do you like the theory on this? Do you sense that even without like having to check the answer or something like that, we're right about this? I have a couple visual aids to help us understand this for those of us who are visually challenged. This is the kind of thing that might be like hanging in a grocery store during the holidays or something like that. It's a pink bell. I don't know why you would want a pink bell, but I hope this helps us to understand the process that we're going through. I'm going to pass this around. You can play with it. We'll talk on, right? Come on. Do you think that would be a fun thing to calculate the volume of using calculus? I do. The only thing we need is a function for that edge of the curve there, which we could do. Yeah. So I'll pass that around and you can play with it. It's so fun. Pretty good job. Have fun. Let's see, do I have any other fun things in here? I have other things for other days, but that one, no, not today, not that one. Oh, here's one. Oh, Valentine's Day. There you go. You guys can play around with that heart. Come on, that's fun. What's going on here? Okay, that actually, there are a whole bunch more fun toys in here, but they are, I think we have to wait. Those are for another day. Sorry. This is very exciting, but just those two for now. We get those passed around. I do have one other fun thing. And actually, this is a miss on my part. In the past, I've always like kind of said, hey, this is not the end of a rocket. This is like the end of a potato, right? And you can imagine that when you're cutting this, it'd be like kind of creating potato chip slices, right? So it's a stretch, but I have potato chips for you. Can you eat? You can?
Yeah.
Is it? Well, I just thought you were a big class. All right. While we do this, I have another one for you, and I'd like you to give it a try. Oh, I just realized I have one more miss in our lives. I don't know how important this is, but I did have a note for you that has these 3 problems we're doing today on that stuff. I don't know that it's. I don't know why we have a note sheet here, but this has the 3 problems we're doing, including the one that's on the board. So you can go ahead as I distribute some chips. It will help you remember. This is okay. We have to make mathematical connections with it. It'll help you remember that when we slice something, we get these very thin discs, which is what chips are. By definition, they're very slim, thin slices of a solid. Anyone? Do we have any 3D printer people out here? How does a 3D printer break down your model, preparing it for print? Have you ever seen a 3D printer do its thing? Math, yeah. No, of course it. Yes, it divides it into layers, right? Thin layers, and And you can even see if you watch the software on these things print it, it'll like actually show you which layer it's printing. And is it actually a perfect, smooth, solid, continuous in every way? No, it's actually a very, very finely discrete thing that appears to be continuous. And that's all it's doing. It has a very thin layers. And then in the end, they're so good. I mean, I have something here, I'll pass this around. This is one of my favorite 3D printed objects here. I'll show you. It's sorry, we're getting a little off track here, but that's okay. I'll show it to you up here, and then so you can see what to do with it. And then when it comes to you, you can try it yourself, because it's not obvious. You're like, that looks dumb. But I promise, it's mind-blowing. Are you ready?
Yes.
Are you ready? Are you emotionally prepared for this moment? Okay, this is a 3D printed object, and you can actually see if you look really close to that very, very thin layers where it's printed. So, hello class. Am I upside down? Are we good? I'm upside down.
Oh, wow.
It's okay. It's not a problem.
Mostly just left it like that.
Okay, and you're on, Callie, too. All right, so the first way I want you to look at this, I want you to think of it. Can you see what this looks like? What is the cross section of those? Yeah, they look like diamonds or squares or something, right? Circles. Anyway, it's 3D printed, but yeah, it's an illusion. It's an optical illusion. When you get it, you'll see that it looks like diamonds from this side. Looks like circles from this side. Anyway, so I just wanted to give it before you get to it. So that's what you should do is kind of look at it like this and then turn it. What? That's what you should say. Okay. All right, back to our. But actually, after you're done being mind blown by that, then also see if you can look and look very closely. It's the only thing I have. Actually, I do have some other 3D printed objects here. See if you can find the layers in these. This is my 5 platonic solids. Again, it's nothing really to do with today's lesson. You're on.
Wait.
Jackson, it's your time to shine.
This is your time. This is your moment. Okay. So you can pass around the platonic solids as well, just so you can see. All right, now we're done. You were, yeah, that was your moment.
Shining star.
All right, so let me get some potato chips out to you. Remember, you're only allowed to eat them if you're thinking about calculus. Okay, that's the rule. Okay. Anytime you eat chips now, for the rest of your life, you have to think about calculus. It's the rule. You have to agree to that in order to eat chips today. So you have another problem on here. Have you begun it? The first thing to do would be to visualize it. Number 2, right here, we're now doing root x again. Y equals 1 though, and x equals 4 about the line y equals 1. So I want you to think hard about what your expression, in particular, what your expression for the radius will be. And we'll go over it in a minute.
Yeah, it's bounded by y equals root x and the line y equals 1.
And then, like, I didn't have enough and I
Tiny section on the end
literally
of the
just print out a page and cut them all.
is not bounded by x equals 4.
I think because it's for me. Maybe it's me.
Because it's not. What is all we know?
Is everyone getting the heart and the bell? Are they coming around? Hopefully you're. Maybe I'm not going to hear you. These are good for you. Think about that. So that's a lot. Okay, there you go. Camera can spread out. You don't want it?
Cameron, did you break it?
Sure.
Hey.
Small DX cylinders of potato.
Why though? I don't understand.
Yes. Oh, yeah.
Eat those and get you some. Alright, I'm coming back in the room. I'm coming.
I feel bad because I remember the other day in the comment I found in the video and then she was this is why wait, I was like, yeah, I remember that.
Just at 8 o'clock in the morning. Are you thinking about have you been able to see on the 3D printing things that are coming around? Can you see the little striations very small?
How come you almost support actually? Then another half of the time, I was squeezing this over at the very last second. I'll just see what and flash.
You sure?
And then I still had all these skills.
Really?
How's this problem coming? Did you do it yet? Here, let's go over it and then I'll distribute a few more here. I've got half a bag left. All right, so as usual, you need a picture of this. So the region here is, of course, this one right here. I didn't mark it. I should have shaded it in or something, but it's this one here. There's only one unique region we could be talking about that's very nice. That has boundaries given by these three functions. So it's this region here, and that's the slice. When we rotated it again, it looked very similar to the last one. It maybe is pointier though. I don't know. I just stole the last picture, but it's actually probably a little pointier. We'll actually maybe after we're done with these problems, we'll go back to the Apple maybe and plug them in. We can check our answers. We can also see an really accurate picture of what both of these look like. So we need an expression for R and H. Of course, H is still what? Dx. What's R though in this case? Help me out. Yeah, we got to measure this distance. For a given value, how would you actually measure this radius? And keep in mind, since this is the axis of rotation, y equals 1, we're trying to figure out how far away is the edge of our object from this axis of rotation, right? This axis of rotation, y equals 1.
Why aren't we worried about what's below it?
So it's this distance, huh?
Why aren't we worried about what's below it?
You mean down, or wait. Well, I guess the thing we're trying to visualize is this piece, forget this part.
Okay.
This piece rotated around this line.
Just forget it?
Huh?
Just forget about
Exactly. There are other parts of this curve over here that are being forgotten too, and we should feel bad about them, right? So that distance, how would you calculate it? If you were at like 2.4, well, I think you would find this y value, is what Shimani's saying, which is root x, and then you would minus 1. You subtract 1. So I think we have a radius and a height for us, and now we just integrate. The one thing we need to do, remember though, is also correctly choose the limits of integration, and those are like just short of being trivial on this one here. It's not. We have to think about it a little bit maybe. What are our limits of integration here? Yeah, 1 and 4 this time. Yes, Jackson.
Why wouldn't you worry about the stuff on the bottom? Like if you're rotating the whole function, how do you know?
We're not. We're just rotating this piece of the function.
How do
Right?
you do that?
Well, because the region that we defined is actually, and I shouldn't have drawn these other parts, doesn't include this and this. I mean, by the same logic, on the last problem, you should have been worried about like the rest of the square root function. Doesn't that get rotated too? Like, well, I guess sure. We just don't care about that part, right? Because that wasn't the question, you know. Yeah. So I think it might be good actually right now, even just to fire up that other applet here again. Let's go back here and plug this one in. Let's do this one. We don't have to go back and do the last one maybe, but I think it might be good just because some of you are having trouble visualizing this. So square root of x from 0 to, we're doing from 1 to 4 here. Set to, okay. We should set the window to -1 to 5 maybe. And so actually this is a lot thinner than we might like, right? And y equals 1 also. Oops, 1, I meant. And we're going from 1 to 4. We're going to go across the line y equals 1. Okay, so are you ready? And over here it should compute the volume. What did we get? 3.665. Let's check. This is a big moment. Can you see the region we're interested in? So there it is, almost done. So you can kind of see it's actually, that's a better picture than what I have in the PowerPoint. It's kind of a pointy thing, right? And what about this? A couple of you are saying, like, what about the other part of the square root function? Well, what about it? I don't know. It's just not part of the question, sorry. Right? But does that give a good visual? And did we get the right answer?
Yeah.
3.665. Yes, good. Okay. Good. Questions on that one? We good? Notice here that we just use FNA, right? You could actually do that one by hand, though. Could you? How would you have to do it? Yes, true. You might have to multiply it all out, right? And then you'd have this power rule on a bunch of stuff, right? You could do it. All right, let's take a look at this one too, very carefully. The region, I feel bad. We should have not had the region on there because it makes you think that that's an easy part of this task. When in fact, drawing the picture is sometimes the hardest part. In fact, I'll just tell you right now, the place where people lose the most point, well, I should say the most points, but often people lose a point or two, or a lot of points, on the quiz and on the test in this unit is when it comes to something like that, like the last one, where it says like y equals 1, x equals 4, they draw like x equals 4 as a horizontal line or something like that. Can you believe that? Calculus students graphing x equals 4 as a horizontal line. Don't let it be you, okay? But that always happens. Then as a grader, it's very difficult because you have now constructed for yourself a problem that is like basically a completely different problem. And so it's hard for me to give you very many points. So just be very careful about your algebra 1 skills when it comes to like drawing lines in your graphs and picturing these things. So that's what I said. My apologies for already providing these pictures for you on this. That's part of the important work to do here. So this time I think it's pretty clear we're going to be rotating around the y-axis, and so our discs this time are going to be horizontal. Okay, we're going to be going this way, and so we're going to get discs again. It's going to be beautiful. We're going to have all nice cylindrical discs. It's going to be wonderful. I can already picture it in my mind, you might say, how this is going to look. We can fire this one up in the applet too. It allows us to do it around the y-axis too. And let's just kind of think about this representative slice here. Again, we're kind of slicing this way now. And that has, this time we might say, a width of, or a height of dy, right? So we need expressions again for r and h in terms of y, this time, in terms of y instead of x, okay? So we've already said what h is here, the height or the thickness of the disk is just dy, that makes sense. What about the r value? Well, we've already done a little bit of the hard work of giving it to you. At first you were like, I don't like that. I really don't like seeing it this way. But actually we're doing you a favor because that is already r, isn't it? What are the limits of integration? Again, for these first kind of problems, we haven't done too much in terms of pushing you too far. The limits of integration are, I think, somewhat clear, just from even the picture we provided or from the problem statement up there. So, don't you finish that one off by hand? Just to practice your integrals. I'll put the rest of the solution up here in a minute. But are you okay with this integral setup? 1 to 4 pi r squared dy. What's r? 1 over root y. Again, we're doing you a favor by giving you this crazy function, because when you square it, you get something nice, and you know the integral of 1 over y. So work it out just for fun. See. So remind yourself of how to do integrals while I bring the work to the people who see what you need. There you go. Think about that. Deborah, you sure? You sure? They're good. How's that
Maybe don't clean it and then forget to take it out.
So last month, then I completely washed out and I left it till like that. I still tastes like soap. And like this water bottle, I filled it and drank it like 5 times.
That's why I need like the really nasty like Gatorade powder that never gives you full flavor. I'll take some.
I know, right? Where's your sodium intake for the week?
Okay, so basically, whenever you put water in my water level,
Did you figure it out? Integral of 1 over y. Antiderivative, plug in 4, plug in 1, subtract. You got a pi in there too, don't forget. What function are we looking at here? Antiderivative 1 over y. 1 over y is what? Natural log. Yeah, absolute value of y, but we don't need it. You know, we can just say absolute ln y here because the limits of integration are positive, so that's okay. I'm gonna ask you that maybe you guys can make sure the trash gets in the trash can so that it agrees. And then what's the natural log of 1?
0.
Okay. I just want to remind you of that. Did you get pi times ln 4?
Yes.
Or you could write 2 pi ln 2 if you want. Whatever. Either one of those would be acceptable answers. Hopefully you understand why they're the same. So I just thought it would be a good exercise to remind yourself of a little bit of the integration techniques that you are expected to continually know forever and ever. Amen. Anything you want to talk about on these 3 examples? I've got one more for you that's not on the sheet that, I don't know, has a very strange real world feel, but we'll give it to you. I don't think it's on the back, right? I think this is just one side. I'll give you a chance to digest what we just did. So this goes back to yesterday too. Some of you were thinking like, I don't really like integrating with respect to y. You really just need to kind of see that it's useful and like get to the place where it's visually something you can handle and you can integrate with respect to y just as easily as you can with x. It's not hopefully too uncomfortable for you. I need you to become comfortable with that. Thinking in terms of y. Okay, well then, let's look at this last one, which is close to my heart. I grew up in central Pennsylvania, right here in 3 Mile Island. So we got a little cooling tower action here. There's one tower at 3 Mile Island that had a meltdown in 1979, and so the reactor that is associated, I guess, with that tower. And so you can actually walk underneath of it. The other ones are active. The steam in these are like thousands of degrees or something, so you don't walk. You wouldn't want to walk into a tower like this one. But there's one that's not working, and the other 2 are piping smoke, piping steam into the air. But the other one you can walk under it. It's beautiful to look up inside of it. It's just a gigantic concrete structure. And the way it looks, by the way, these are this equation is probably not super accurate. It's actually a hyperbolic.
Good morning, Richard Montgomery.
sheet.
These are your morning announcements. Please stand for the pledge.
Okay,
I
let's do
pledge
that.
allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Please be seated.
Are we not having Army standard.
Congratulations to the RM debate team on their third consecutive county championship. Special congratulations to Danny Espejo and Nam Lam on the dramatic victory in the semifinals. The Minority Scholar Program's 7th annual retreat is March 3rd, 2018 at Watkins Mill High School from 8 to 4. The cost is free. Please join us at the retreat to learn what you can do to help us in closing the achievement gap. You must register online to be counted. Bus transportation is free. T-shirts and sizes are needed, but more importantly, you are needed. Permission slip forms should be available February 16th and returned to Mrs. Boyd by February 27th. Adult and student concession volunteers urgently needed for basketball playoff games this Friday, February 23rd and next week. No experience required. Game times have changed, so please check the website. The Red Cross Club is collecting items to help Rockville's Rainbow Place Women's Shelter. They need paper products like plates, bowls, napkins, and cups, and plastic products like utensils and zip-up bags. Please bring donations to room 219 by this Friday. Thanks for supporting Rockville. In recognition of Career and Technology Month,